My name is Elliot Chu, and I'm the Interim Dean of the College of Science at the University of Arizona. Today's lecture is called Water, the Colorado River. Our lecturer is Connie Woodhouse, who came to the University of Arizona in 2007. Connie is a professor in the School of Geography and also a professor in the Laboratory of Tree Ring Research. In 2020, she was elected as a University of Arizona Regents Professor. Her topic is on the Colorado River and what a vital resource it is for the arid Southwest, including Arizona and LA County. Currently, the demand on the Colorado River exceeds the supply, and Connie is going to explore the impacts of natural variability and climate change on this important water supply.
Hello everybody, this is the third talk on water for the College of Science, and it's on the Colorado River. This week we're transitioning from Diane Thompson's talk on the oceans, and in particular the Pacific Ocean, and we're moving to the continent to the east, to North America, and to the Colorado River Basin. The Pacific Ocean is really important for the Colorado River Basin. It is the source of water for this really important river. If you look at the image to the bottom right of the screen, you can see the Colorado River from space, and you can see it's going through a very, very arid region, and so that water is very, very critically important for this arid region's river. You may have seen some headlines in the news over the last couple of months. They say things like Colorado River watershed forecast looks very dry for 2021. The impacts of warming are being evident. And it seems like this situation could be quite dire for the Colorado River. So what's the story here? Well, it's true. We are in a drought. Warming temperatures are impacting the basin, but there's other factors going on as well. We're living with a legacy of allocations that were made 100 years ago, and this river is an arid lands river, which is really important for this region. The Colorado River is the most important source of surface water for much of the Southwest. It's really important for the population. It supplies water for over 40 million people in the basin and urban areas outside of the basin. It supplies irrigation water for over 4.5 million acres of irrigated farmland and ranch land. And it supplies 5 billion kilowatt hours of electricity through its dams. In Arizona, the Central Arizona Project brings Colorado River to much of the state's population. About 80% of the population gets some of its water through the Colorado River. Most of the water, though, is from high in the headwaters, about 90%, and it flows down, and most of the water use is in the lower areas. Now, this isn't unique for rivers in the West United States. This is often the case where the mountain headwaters, like the Sierra Nevada, support the urban areas that are downstream. What is unique about this river is that it flows through a very, very arid landscape. For a river this size, its flow is relatively low. So, for example, the average annual flow for the Colorado River is about 1,400 cubic feet per second. If we compare that to the Columbia River Basin, which is about the same size basin, slightly larger but a shorter river, the average annual flow for the Columbia is 273,000 cubic feet per second. So the Colorado River really has a fairly limited water supply for the size of the basin that it is. The Colorado River is one of the most developed and managed rivers in the world in an effort to spread its limited water supply as far as possible. Dams and reservoirs, canals, and trans-mountain diversions are all built infrastructure to distribute its waters. One of the other unique aspects of this river is how much storage it has. The Colorado River system has enough storage to supply about 4 to 5 years of average annual flow, which is really, really quite unique. There are also canals that bring water over desert areas to support urban areas, like the Central Arizona Project brings water to Phoenix and Tucson. The Colorado River Aqueduct brings water to Southern California. Another aspect are the trans-mountain diversions. These bring water from the upper Colorado River Basin to the Arkansas and the Platte River Basins, initially to support agriculture and now to support urban growth in the Colorado Front Range. Okay, let's look at the geography of the Colorado River Basin. The little map in the upper left shows where the basin falls. It's within seven states. The headwaters are in Colorado, mostly in the Colorado Mountain, Colorado Rockies. The headwaters also come from the mountains of Wyoming and Utah as well. The water flows out through the Sea of Cortez, although it's been several decades since the river's water has actually flown to the ocean. Lee's Ferry, which is that point in the middle, is the divide between the upper basin and the lower basin. And Lee's Ferry is very important. I'll be talking about Lee's Ferry in this presentation because it's the gauge that is measuring upper basin flow. And as I said, most of the water comes from the upper basin. The other two important features are the two main reservoirs in the system, Lake Powell, which is just above Lee's Ferry, and Lake Mead, which is outside of Las Vegas. And these two reservoirs are very important for the management of the river between the upper basin and the lower basin, and also to fill the compact with Mexico. So why is all the water coming from the upper basin? Well, it has to do with topography. So this map is a topographic map of the western United States. The high elevations are those sort of blue to light blue colors. The Colorado Rockies reach peaks of 14,000 feet or higher, and that's where the headwaters come from. And the lowest elevations are less than 300 feet down there by the mouth. This pattern of topography closely mimics the pattern of precipitation. So here's a precipitation map, and you can see places that are green and blue are where we're getting most of the precipitation. In fact, in some of those areas, we're getting over 7 feet of precipitation in a year, versus the very brown parts of the basin, which are 4 inches or less. So again, what we're seeing is that most of the water comes from these high elevation headwaters. In fact, 3 small subbasins, the Yampa, the main stem of the Colorado, and the Gunnison, contribute about 40% of the flow of the entire river. So we're seeing that much of this water, almost all the water, comes from the high headwaters, while much of the demand is down, the human demand anyway, is down in the urban areas and the agricultural areas that are at lower elevations. Now the headwaters have users of water as well. We have ranchers and farmers. Tourism relies on this water as well as the natural systems. So we have this tension between the supply and the demand. And this tension was realized early on by people like John Wesley Powell, who was one of the first to explore the Colorado River. In fact, he took a trip down the Grand Canyon in 1869. He also had multiple subsequent trips which explored this area. And through his travels, he formulated ideas about the water management of this region. He became the second director of the U.S. Geological Survey, and in that capacity, he addressed an audience of Los Angeles farmers and developers in 1893. And this is what he had to say to them. There is still not sufficient water to irrigate all this arid region. I tell you, gentlemen, you are piling up a heritage of conflict and litigation over water rights, for there is not sufficient water to supply these arid lands. So that was in 1893. I'm going to turn now to the Colorado River allocation of water resources, its development, and a role for tree rings. In 1922, the Colorado River Compact was negotiated. These gentlemen here, the Colorado River Commissioners, allocated the resources in the river according to what they thought existed at the time. And of course, they were looking at a gauge record that was pretty limited. There was some politics mixed in there as well, but what they did was they allocated 7.5 million acre-feet to the upper basin and 7.5 million acre-feet to the lower basin. Now, a million acre-feet is the unit that water managers use in the western United States. 1 million acre-foot equals the amount of water that would fill an acre to the depth of a foot. And it's about the water that 1 or 2 families use for their inside and outside water needs over the course of a year. So we had 7.5 million acre-feet to the upper basin, 7.5 million acre-feet to the lower basin, and in 1944, the Mexican Water Treaty allocated an additional 1.5 million acre-feet to Mexico. So the total allocations equal 16.5 million acre-feet. I want you to keep that number in mind as we go forward. The question is, though, is 16.5 million acre-feet a reasonable amount of water to allocate on an average annual basis? Well, as the 20th century unfolded, the gauge record became longer, and we were able to assess this question a bit more. But also over the 20th century, over this period of time, tree rings were being developed as a proxy for stream flow. And that work was being pioneered at the University of Arizona's Laboratory of Tree Ring Research. Edmund Shulman was the first to really look at whether tree rings could be used as a proxy for stream flow. He started in the 1930s. In 1944, he came out with a report that documented this capability. But in 1942, he did a report for the Los Angeles Bureau of Power and Light, which showed how tree rings could be used to document stream flow going back to 1366. Now, this is an early indication that resource managers were interested in understanding if the gauge record really represented how the stream flow had varied over a longer period of time. So I'm going to talk a bit now about how we use dendrochronology, the science of tree rings, to extend the hydrologic record back in time. So what you're looking at here is a cartoon of a conifer with a pith in the middle, the bark on the outside, and you can see the annual ring widths. Now, these annual ring widths vary in their width, and the variations are responding to the environmental conditions that affect tree growth. In the western United States, most of the time, these ring widths are varying due to climate, and in the arid Southwest, those variations are due to moisture. So in a wet year, we have a wide ring, and in a dry year, we have a narrow ring. So if we're interested in getting records about past hydrology and past moisture, there's certain trees that we target because we know that they're extremely sensitive to variations in moisture, and they'll record that in their rings. We tend to sample things like Douglas fir, pinyon pine, and ponderosa pine because these trees often grow in very arid locations. They're growing on sites where there's not much soil or they're being stressed by climate. So what we're looking for are relationships that look like this. We have the ringwits of one tree in green, shown with the average annual precipitation in western Colorado shown in blue, and you can see how well they track each other. The trees are not rain gauges, of course, but they're tracking variations in precipitation very closely. However, we're not interested so much in precipitation here, but in stream flow. So how does that work? So what's going on here is that the annual ringwits of trees in this area are very sensitive to the amount of moisture at the beginning of the growing season. And what controls that is really the cumulative climate over the course of the water year, which is the beginning of October through the end of September. So the trees are responding to those cumulative conditions, but mostly to winter snowpack, because that's the most important source of water for that soil at the beginning of the growing season. In a similar way, annual stream flow, again for the water year, is reflecting the cumulative conditions over the course of the year. But it's winter snowpack that makes the biggest contribution. So it's the winter snowpack that is integrated both in the annual ringwits and the annual stream flow that makes it possible to reconstruct stream flow from tree rings. It's an indirect relationship, but it's quite robust. So if we're interested in collecting samples to reconstruct stream flow, we go out in the field and we target these trees from these species that are sensitive to moisture in the area, in the watershed or the climate shed of the river that we're interested in reconstructing. We sample about 20 trees per site, and we take increment cores from living trees. So what you're looking at here is the end of a increment bore, which has a sharpened end at one end and has a handle on the other. It's inserted into the tree to pull out the cores from the living trees. So we sample living trees with an increment borer, and the oldest living trees that we can sample in the Colorado River Basin at least date back into the 1100s. So one of the trees that I sampled. It's a pinyon pine and dates back to 1160. If we want to get our record of tree ringwits back further in time, though, we can use dead wood. Lots of wood remains on the landscape for hundreds and hundreds of years, and we can augment the living tree record with this dead wood. So how that works is that we take a sample from a living tree. We know the dates that that tree lived. If the ring pattern overlaps in time with the dead tree that we've sampled, then we can determine the dates for that piece of wood. And then if an even older piece of wood overlaps in time with that chain of trees that we've dated from the living tree, we can then continue to extend that record back in time. And so in this way, we can build a record that's much longer than the living trees will provide us. So once we've sampled our trees with an increment borer, we've cut our cross sections from dead wood, we go back to the lab, we sand everything down, and then we date each and every ring to the exact calendar year. After all the rings are dated, we measure them using a system that looks like this. It's a microscope with a sliding stage. Each and every ring is measured. This is a great way to introduce undergraduates to the lab, as they are quite good at measuring rings. Once we have all the rings measured, they're all averaged together to create a site tree ring chronology. And the chronology is the unit that we use then for reconstructing things like stream flow. So to go from tree rings to stream flow, we're actually calibrating annual ringwits with an annual record of stream flow. We create a statistical model in which we're estimating stream flow from tree rings. And the model is shown here. The gauge record is in gray, the reconstruction is in blue, and you can see how good a match it is. That's not always the case. We're quite lucky in the Colorado River Basin that the trees are really replicating what's going on with the stream flow. So the model is actually an equation, and we plug in the tree rings for their length of time and then develop the full reconstruction that looks something like this. So you can see here a Colorado River reconstruction going back to 1490. In this case, this one goes up to 2005, and then you can see the gray record is the instrumental gauge record, and the match is quite good. So using these methods, the first reconstruction of stream flow was generated by Chuck Stockton and Gordon Jacoby. Now, Chuck Stockton was at the University of Arizona Laboratory of Tree Ring Research. His colleague Gordon Jacoby was at Columbia University, and they were the first ones to apply these methodologies to reconstruct stream flow, and their first reconstruction they developed was for the Colorado River. So this is what their reconstruction looked like. It goes from 1564 to 1962 and has three important features. The first is that the long-term average is 13.5 million acre feet. Now, if you remember how much was allocated, you'll remember it was 16.5 million acre feet. The second aspect is the date of the Colorado River Compact, which was 1922. You can see that the stream flow for the 2 decades prior to the compact drafting was quite high. In fact, it's higher than anywhere else in this record. And the third thing you can see is that there is a very severe and sustained drought in the early part of the record. So in effect, the Colorado River was allocated with streamflow that looked like this kind of flow on the right. And in fact, at certain times in the past, the streamflow has looked more like this on the left. So Stockton Jacoby realized the implications of their reconstruction, and this is what they had to say in their report. They said the general picture of a collision between water demand and supply in the upper Colorado River Basin in the not too distant future is all too apparent. Now that was in 1976. In the decades that followed, though, there was a lot of growth and development, especially in the urban areas that were receiving Colorado River water. There didn't seem to be much acknowledgement, or any acknowledgement at all, there might be a problem about overallocation. Things began to change at the beginning of the 21st century, and there were three major events that were really important in this regard. The first was a period of sustained drought began in 2000. This drought was particularly severe from 2000 to 2004. That 5-year period was very, very dry, and we saw iconic photographs like this where we had reservoir levels drop down. We saw boat ramps high and dry. That drought is continuing at this point. There have been no years of more than 1 year of above average flow since 2000. The second thing that happened was that Lake Powell levels dropped very rapidly. Starting in 2000, the reservoir levels dropped extremely rapidly, reaching a low of 33%. You can see that there's been some recovery since then, but it really hasn't recovered. And right now, the Lake Powell levels are at about 42% capacity. This steep decline in reservoir levels was quite an eye-opener for a lot of water managers who didn't anticipate the reservoir could drop this fast. The third thing that happened was 26 years after Stockton Jacoby made their forecast, the Colorado River demand has exceeded supply. The red line here going upwards is the 10-year moving average of water use, and the blue line is the 10-year average of water supply starting from 1923 and going forward in time to about 2010. And those two lines crossed in 2003, and you can see they have remained crossed. The reason this hasn't been catastrophic is because of all that storage in the river system. So at this point, we have a convergence of overallocation, of drought, and climate change. So I'm going to leave that thought for now and talk a little bit about the variable water supply of this river in a changing climate. As you've seen from the reconstruction of Stockton Jacoby's, this long-term record of streamflow is extremely variable, and that reconstruction shows a lot more variability than we see in the gauge record alone. What the tree ring record is documenting is the natural variability of the system, because that the river has varied in the ways that are documented in the reconstruction in the past. We can expect under natural variability alone for the river to vary that way in the future, including those periods of drought. However, we have climate changing now, so along with the natural variability, we're going to see the effects of climate change on the river. So what I want to do at this point is first talk about the reconstruction of streamflow and that part of the natural variability, and talk about how climate change is impacting that. So first I'll talk about the variable water supply, looking at the gauge record and the reconstructions. This is the gauge record of Colorado River at Lee's Ferry from 1906 to 2018. It's the estimated natural flows, which means it's had the effects of diversions and depletions removed. This is something that the Bureau of Reclamation does so that we can see how the natural variability of the river without those management effects. This record is in million acre feet, and you can see that the average is just under 15 million acre feet. It's 14.8 million acre feet, which, again, you might note is less than the allocation of 16.5 million acre feet. This record is highly variable. You can see the lowest year was about 1977. It was about 5 million acre feet. The wettest year, the highest flow, was in 1984, just a little bit less than 25 million acre feet. These individual years aren't really of concern because this river system has so much storage in it, but it's the multi-year droughts that are really more of concern in this river system. These are the droughts in this record. Drought being defined here as consecutive years below the long-term mean, broken by no more than 1 year of above average flow. So most of these droughts are on the order of 6 to 9 years, but you can see the most recent drought, the drought we're in now, started again in 2000 and is continuing now, even though we don't show that record. 2019 was a wet year, but 2020 was very dry, and 2021 looks like it'll be dry as well. What you also might notice is that the early part of record has no droughts. It was a period of relatively high flow. Again, this is the period of time on which the Colorado River allocations were based. So the question from this record is this representative of the long term? Is this an unusual amount of variability in the record, this wet period, these droughts, or is this what we have seen over past centuries? I'm going to be talking about a different reconstruction of Colorado River streamflow here, one that was updated from Stockton Jacoby's work. The work was done by my colleague Dave Miko at the University of Arizona's Laboratory of Tree Ring Research, along with myself and our colleague Steve Gray. We extended Stockton Jacoby's record back in time to 762, again using that remnant material to get that record back in time, and brought it up to 2005. So it's much longer than the gauge record and quite a bit of an update from Stockton Jacoby's work. We can look at the record of droughts in this reconstruction, defining drought the same way that we did for the instrumental record, and we can see that this record just has many, many droughts. It's just a characteristic of this stream flow. But you can see that there are variations in the distributions of these droughts. There's periods that lack droughts, like in the 1500s, and there's fewer droughts in the 20th century. You can see where there's periods of more frequent droughts and longer droughts. The longest drought in this record is in the late 1200s, and it was 25 years long. It coincided with the period of time that we know the ancient Puebloans dispersed from the Four Corners area. While drought certainly had something to do with this dispersal, there were certainly other factors involved, though we know that many of them moved to areas like the Rio Grande Valley where water supply was more reliable. So drought duration is one important characteristic of drought, but there's other characteristics that are also important, like intensity. Duration plus intensity gives an overall severity of a drought event. So I'm showing you here a different reconstruction of streamflow, one that's updated to 2014. So it goes from 1116 to 2014. And I'm showing you the duration of droughts on the bottom axis from 2 years to 14 years, and the intensity of drought, or the average annual streamflow, on the y-axis. And we're defining droughts here in a slightly different way. These are just consecutive years below the long-term average. The cluster of points represents all the droughts in this record, but the brown ones are the droughts before the 20th century, and the purple ones are the 20th and 21st century droughts. And you can see from this record that droughts that were prior to the 20th century have been more severe of any duration, and we've had droughts that have extended up to 14 consecutive years in this record. We haven't seen that in the modern period of drought. So what about wet periods? This is the same reconstruction, smooth of the 20-year running average, to look at the wettest 20-year periods. So you can see that the wettest 20-year period occurred just after the turn of the 1600s, so it was following Stockton Jacoby's long drought. The second wettest 20-year period followed the drought that coincided with the dispersal of the ancient Puebloans. The third wettest was the early part of the 20th century. I was starting to look at the 5 wettest periods, but I decided to look at the 6th, because you can see the 6th wettest period was actually the end of the 20th century. So if anything, the 20th century is characterized by wet periods rather than dry periods. And if you'll remember, a record of drought also showed fewer droughts in the 20th century, suggesting that if anything, the 20th century has been wetter with fewer droughts than any century in the past. So the trees give us this record of long-term variability, but let's look at how the climate is changing and sort of interacting with that as well. So I want to talk about the major climatic influences on streamflow to start with. This is a study that I did in 2016 with a number of colleagues, and we're simply looking at the major climatic controls, the major seasonal climate controls on streamflow, what was important for regulating, what was important for explaining the variability in streamflow. So you can see that October through April precipitation, that's the cool season precipitation, accounts for about 2/3 of the variability in annual streamflow. Temperature, specifically March through July temperature, explains for 8% of the variability in streamflow. And 2% of the variability is explained by the soil moisture in November, before the snowpack season really begins. About 1/4 of the variability is not explained by climate, and that's due in large part to the base flow in the system, or the groundwater component. Cool season precipitation is very important, but temperature is important as well. So of all of the precipitation that falls in the basin, only 16% actually makes its way into the river. Where does the rest of that moisture go? Well, it's lost mostly through evaporation and transpiration from plants. And those two factors, evapotranspiration, are highly regulated by variations in temperature. Let's take a look now at the trends in precipitation and temperature over time. So this graphic here shows trends in precipitation starting at the turn of the 20th century through about 2017. The annual values in the gray line, the blue line is smooth, but that dotted red line shows the long-term trend. And in the case of precipitation, you can see it's flat. There's no trend in precipitation. What about temperature? Well, we see there is an increasing trend in temperature. Temperatures are warming in the basin. So with precipitation having no trend and warming temperatures, what will we expect to see from streamflow? Well, streamflow is actually decreasing in time. So over the last decade, instead of 16%, we're only seeing 14% making its way into the river. So that's the effect of temperature on precipitation's efficiency for finding its way into the river. What about the future of the Colorado River? There's some things that are certain and some things that are less certain. One thing that's certain is that temperatures will continue to warm in the basin. These two graphics show projections into the future over the next 100 years. All the squiggly lines show the different model runs, and the heavy dotted line shows the average of those runs. We're looking at two different scenarios. The top scenario is a moderate emission scenario. The bottom is a more extreme scenario. And the baseline we're looking at here is the difference from 1971 to 2000. In both cases, temperatures are warming. It's just a matter of how much warming will occur. What about precipitation? Precipitation changes are less certain. These are the same kind of diagrams, and we're seeing the spread of the model runs and precipitation. That dotted line is showing a slight increase in precipitation over the 21st century. And how does that translate to streamflow? You can see that the cloud of lines has become broader, but that average line, that dotted heavy line, indicates that Colorado River streamflow will decrease over the 21st century. These graphics are from a report that was produced a year ago. It was called Colorado River Basin Climate and Hydrology, the State of the Science, and it was a synthesis of all available science at the time. I had the privilege of being involved in this study, but I wrote the chapter on the paleoclimatology. The report summarizes the future of the Colorado River quite nicely, so I'll read a little bit from the report. It says nearly all the many data sets show a strong tendency towards lower annual runoff volume in the upper and lower basins. However, it says that the spread of potential futures, in terms of the hydroclimatic changes, may not be appreciably reduced. We may not get more precision on that because much of the spread is due to the unpredictable nature of climate variability. So on one hand, we have those projections from our models, which are really valuable because they show the warming, but we also have that spread of natural variability from the treeing record. So together, those two pieces of information are critical for anticipating the streamflow in the future. This arid lands river is critically important for both human and natural systems. It's the primary source of water supply. It's high in demand. Coupled with that is that it's overallocated, that natural variability is a part of the natural climate system here, that we have warming temperatures, and we have drought conditions. Droughts will occur in the future, but warming temperatures will exacerbate those precipitation deficits. In the most recent drought over the period of 2000 and 2017, Colorado River streamflow decreased by 16%, and studies show that half of that decrease was due to warming temperatures. Make no mistake about it, the impacts of warming on an already over-allocated water system are going to present huge challenges. Terry Fulp is the recently retired director of Reclamation's Lower Basin Colorado River region. He was interviewed recently about the future challenges that were being faced by the Colorado River, and he had this to say: "I would say that the problems are only going to get harder, and the way to solve them is to communicate and collaborate. That's the only way we'll be successful." So I've been encouraged to hear about ways that people in the basin are coming together to collaborate. The users and the uses of the water are varied, and so it's a very complex system, and it's difficult to figure out how to meet all of these needs. But there's been a number of different ways that people are collaborating. The largest collaborative effort is the renegotiation of the interim guidelines for the operations of Lakes Powell and Mead. Those interim guidelines were put in place in 2007, but they end in 2026, and so they're currently starting to be renegotiated. And the stakeholders that are involved in that process are everybody in the basin, from the 7 basin states to Mexico to the tribal nations. But there are a multitude of other efforts, large and small, that I'd like to share with you because I think they offer some encouragement. I recently read about a partnership between California and Nevada, in which Nevada was going to help build a recycling plant in Southern California to replenish the groundwater there. That's a pretty big idea, and a much smaller idea in the headwaters is the idea that's being studied to build beaver dams, either human-built or beaver-built, that would slow water loss from these high-elevation wetlands. And then in the Yampa River, they're planting trees along the river to help shade the river. This hasn't been evaluated yet, but the monitoring is going to be soon underway using citizen scientists. A lot of the water goes to farmers and ranchers in the Colorado River Basin. Certainly water could be saved by not irrigating lands. However, doing that is quite complicated. So there's been research recently to look at the effects of temporarily fallowing fields on the viability of those fields once water is available. And finally, I haven't talked about the environment at all here. So this is a photograph of the pulse flow that was sent through the Colorado River Delta in the spring of 2012. This was a joint effort by US and Mexico, but it was also due to the efforts of Dr. Carl Flessa, who's a professor emeritus here at the University of Arizona's Department of Geosciences. The pulse flow was temporary, but part of the agreement was to allow some water to replenish some of the riparian areas in the wetlands to try to restore some of those. The future will be challenging for users of the Colorado River, but my sense is that there's widespread agreement that these challenges need to be addressed. Running out of water is just not an option. Making do with less, probably much less, is the future, and the future is now. Before I end, I'd like to acknowledge some of the people that have contributed to this presentation and to my career in terms of the work that I've done with the Colorado River. I'd like to thank the Colorado River water managers who have informed both the research I've done and my thinking about the science in the context of water resource management. And I've had many, many research colleagues, so I'm not going to acknowledge all of them here, but I'd like to in particular acknowledge Dave Miko and Jeff Lucas. And then finally, I've had funding from the National Science Foundation, from the Department of Interior Southwest Climate Adaptation Center, and the California Department of Water Resources. Be sure to catch next week's lecture. Dr. Laura Condon is talking about groundwater. Her talk is entitled Beneath Our Feet.
Thank you for joining us for the third lecture in our series on water. We hope you can join us next week for our fourth lecture, Water Beneath Our Feet, with Laura Condon. Groundwater is by far the largest unfrozen freshwater resource on the planet, yet it is often overlooked, overused, and misunderstood. Next week, Laura Condon will explore how the water beneath our feet supports ecosystems and human systems alike, and the role that it has to play in our future. Thank you to our presenting sponsor, Tucson Electric Power, and our series sponsors, Cost Communications, Hale'ualoha Companies, Raytheon Missiles and Defense, Research Corporation for Science Advancement, Tucson Medical Center, and Visit Tucson. Your generous support is what makes this series possible.